Last class, we began our work on least squares fitting, and today's class will continue our work on least squares fitting. In the last class, we wrote our own code to fit a straight line to data. We also used curve fit to fit a straight line to data. The examples of data that we thought of in the class and that we thought of in the homework were data on Kepler's law, where, for example, the planetary data on Kepler's law, you could extract the mass of the sun, and data on the expansion of the universe, where you could extract the age of the universe. So those are the projects we worked on last class. A limitation of last class, a serious limitation of last class, is we were just fitting, whether we used our own code or we used the curve fit library, we were just fitting a straight line, so a very simple fit. Another limitation of the last class is that we were just fitting with no uncertainties on the data points. We were just assuming equal uncertainties on the data points. So today's class, I want to move on to more sophisticated fits, meaning more complicated functions that we might fit to data, also meaning that we would incorporate uncertainties on the data, and that we would incorporate the possibility that the uncertainties on the data points are not equal uncertainties on data points. So that's the plan for today. I want to cover two distinct cases of fitting data. There's one case where the function that you're fitting to the data, or we might call it the model that we're fitting to data, is linear in the parameters of your function, or linear in the parameters of the model. So that's one very distinct case where there are analytic solutions to the fit. The other case is where the function that you're fitting to the data, or the model that you're fitting to the data, is not linear in the parameters of the model or the function. In that case, there's generally no analytic solution. We'll do a iterative numerical solution to the minimum chi-square. So those are two cases. I'm going to start with the case of linear least squares fits, and then we'll do the nonlinear least squares fits. So we work our way from the simpler case to the more complicated case. I just wanted to start with this slide, which I showed in the last class as a summary of perhaps when you first meet least squares fitting, this is typically what you first meet. A least squares fit to a straight line, and how to calculate the best fit for the straight line in terms of the data comprising values of dependent and independent variables. So the xi's and the yi's are our data set. Out of that data, we calculate sums of the dependent and independent variables. We calculate sums of squares of dependent and independent variables. We calculate a sum of the products of the dependent and independent variables. And from those, we showed how you can compute the best fit line, straight line through the data. That is the best fit slope and best fit intercept, and the errors on those parameters. And those are these equations here. I still remember this, when I went to college, that it was some sort of ordeal that we had to go through, where we had to do a least squares fit by actually on our calculators calculating these sums of the data points and sums of squares of data points and things like that. Because now we can do this in Python, so it's way easier. Anyway, this is a sort of starting point that we've probably all seen or met before. In the last class, we introduced an alternative way of expressing that least squares fit to a straight line. I kind of summarized it here. So if I was to give the last slope a name for that method or that approach to finding the best fit slope and best fit intercept, I might say it's sort of a summation method. I'm summing up the independent dependent variables and their squares and their products. If I give a name to this method, it's kind of the matrix, vector matrix method or the linear algebra method. So we introduced this method in the last class, and maybe you have met it before, or maybe you haven't met it before. But let me just try and describe again just this language in which we're going to cast this least squares fitting problem in this linear algebra matrix vector method. In this language, the data. So let's take the dependent variables, a set of data points. We think of that as a vector, and we think of it as a vector in a data space. So the data space would be all the possible values of the measurement outcomes. And you've got a set of data, which is a particular vector in that data space. So Y is a vector in a data space. We think of the columns of the matrix M that was the Vandermonde matrix. We think of those as kind of defining the model space. That's the space in which the model exists. And so we're really, when we do a least squares fit, we can write to minimize the chi-squared, we can write it in this fashion here, in this linear algebra approach, where this is a vector in the data space, and this object here, this is kind of its projection into the model space. And the difference between these two is another vector, the residuals vector that we would call it, which is orthogonal to the model space. So that's one way of thinking about this whole fitting procedure is you have some data in your data space. You have a model that defines a model space. You try and fit your data vector to your model space. The best fit is the breadth projection onto your model space, and the residuals is a vector that's outside your model space, and it's a orthogonal to your model space. And so that's the sort of vector language for what we're doing in the fitting. This is just to remind you of all of these quantities that we could write out in this vector language. Here's the dependent variable. Here's the matrix built out of the dependent variable. Here's the uncertainties on the data points, and here's how you calculate the best fit parameters and the uncertainties on the best fit parameters in these rather complex linear algebra equations. So this is how you would extend that straight line fit, whether it's in kind of the summation language, the first slide, or whether it's in the linear algebra slide, to more complex fits. I've given the example here of fits to polynomials. So supposing I wanted to fit a quadratic to my data, or I wanted to fit a cubic function to my data, or some even higher powered polynomial to my data. How would I go about doing that? How would I go about, say, modifying the method that we introduced, the matrix vector method from the last class to do that? How would I go about modifying my Python code from the last class to fit a quadratic or a higher order polynomial? Well, this just summarizes that. It also summarizes how I would deal with uncertainties on the data points, and especially how would I deal with uncertainties if the uncertainties on the data points had different values for different data points. So this steps from a very simple, straightforward fit, where it's a least squares fit with either assumed equal uncertainties or equal uncertainties on the data points, to a polynomial fit of whatever order you like, where it doesn't assume the uncertainties on the data points are equal to one another. So what have I added here? Well, let's take this from here. We still have the vector in the data space of the dependent variable. So that's exactly the same. We still have a van der Waals matrix over here, which is built out of the independent variable as the columns of the van der Waals matrix. But now I've extended it. If you are fitting just a linear order one polynomial, then you just have two columns for the constant term and the linear term. And what I'm writing down here is an example of if I wanted to fit a quadratic, then I would have the constant term, the linear term, and the term depending on the square of the dependent variable. If I wanted to fit a cubic, then I'd have a fourth column here with the cubes. If I wanted to fit a fourth order polynomial, I just put in so this is easy to do in Python. I just put in a fifth column with the fourth column. So that's how you would extend the van der Waals matrix. So that now, this method is very extendable to whatever polynomial order you like. We also said we wanted to extend the method to correctly incorporate the uncertainties, and in particular, the uncertainties on the data points, and if they were different for different individual data points. We do that with another matrix that we haven't yet met. It's this weights matrix here, uppercase W. The weights matrix is just a diagonal matrix. So it's just the diagonal row here, and the elements in the diagonal row are just the inverse of the square of the uncertainties, the standard deviations on your individual matrix, on your individual data. So these sigma 1, sigma 2, sigma 3 are just the uncertainties on y1, y2, y3, the dependent variable. So we just construct this matrix. So this is our starting point. We now need a dependent variable vector in the data space. We need our independent variable matrix, the van der Waals matrix, which really defines the model space. The columns define the model space. And we need our weights vector, weights matrix to handle the uncertainties on the data points. From those, we could just, in a similar way, calculate the vector that contains the best fit parameters. I've got a quadratic in my example, so I've got three best fit parameters. I've got the three coefficients of the three terms in the quadratic, and then I got a covariance matrix that contains the uncertainties on the best fit parameters. Those are the diagonals here. So that's the sigma A, the sigma B, the sigma C. And then it contains also on the off diagonals the correlations between the parameters if they exist. So those are like the sigma AB, the sigma AC, the sigma BC are the correlations of the different parameters. These are was that a question? These are the equations that we use to calculate the best fit parameters, and the covariance matrix, here's the equation for that. They're slightly modified to incorporate the weights matrix. So this equation here was modified, whereas I inserted the weights matrix in this first term and also in this second term. So that's how the uncertainties get handled. And also in this calculation, the covariance matrix, I've inserted the weights matrix here. So this is we said you could derive these equations through matrix calculus. We sort of outline the derivation for the constant uniform error uncertainties case in the last class. These are the corresponding relationships that you derive from matrix calculus if you have different uncertainties on data points. But anyway, this still the expressions for the parameters and their uncertainties is really rather compact, so it's easy for us to use those. Okay, I'm going to go to the code, just show you an example of this. So this code is a modified code, so a code from the last class. Code from the last class was just a least squares fit to a straight line on, I'll call it Hubble data. It was the distance to a galaxy as the dependent variable versus the velocity, recession velocity of that galaxy as the independent variable. And so I had a collection of that data and we fit that data to a straight line. And from the slope of that straight line, we saw the universe was expanding and we saw that we're able to determine the age of the universe. So this is exactly the same data. And I'm just going to use there were two sets of these data. There was kind of a lower Z data, meaning lower recession velocity data, and there was a higher Z data. I'm just going to use the low Z data here. And in the homework, you're going to use the fuller data set with the high Z data. And just trying to remember how to make this larger. Anyway, in this first cell, I'm just again reading in the data like we did in the last class, and I'm just plotting the data to check data looks okay. But I did add one little addition here. When we read in the data in the last class, we stripped out the first and second columns in the data in the file because they corresponded to the dependent and independent variables, the recession velocity and also the galaxy distance. There's a third column in the data, and that's the uncertainty on the dependent variable. And so I've stripped that out too, the slicing, and define those standard deviations or those uncertainties as this little vector here gets. That's the only change I made. We didn't even say in the last class that the uncertainties on the data points were in there because we were just treating the data as if they all had equal uncertainties, but actually they don't. Okay. So then downstairs here is where I'm going to fit this data. I'm going to fit this data, well, now we know how to fit to not just a straight line, but a quadratic or a cubic or any sort of polynomial we like. We also now know how to fit the data to incorporate the uncertainties in the data points. And in particular, we know how to incorporate the uncertainties when they're unequal uncertainties on the data points. So I'm gonna handle both those things. So a few changes I made to the code I used last Thursday, or the cell I had last Thursday for doing the fitting, compared to this revised cell that I'm using for today's fitting. So let me just go through them. The first thing we did in this cell in last Thursday's class was define a Vandermonde matrix. And we just used column stack in the NumPy package to make a matrix out of a column of ones and then a column that was linear in the independent variable data points. I want to build a bigger Vandermonde matrix now because I want to have a column of ones, a column that's linear in the data points. And if I'm going to do a quadratic, I'm going to have a third column that's the square of the independent variables. Actually, I made this so that I could create a, a Vandermonde matrix that corresponded to any size polynomial that I pick, where NP is the order of the polynomial. So here was a modification that I made. I'm still using columns stack, but rather than explicitly listing the columns that I want to stack, the ones and the vector x, I'm going to stack n plus np plus 1 columns. So np is the order of the polynomial. If it's first order, I got 2 columns, so it would stack 2 columns. If it's second order, I'm going to stack 3 columns, and so on and so forth. And I'm generating the columns I'm going to stack. This is a very compact way of generating it. It's going to stack columns that are x to the power pi. And this loop here generates the i's. This for loop here generates the i's. So they're going to run from 0. So the first column that I'm going to stack is the column of x to the zeros, which is all the ones. And then the last column that I will stack is a column, well, at the end, the last value for I in this range here will be NP, the order of the polynomial. So if my polynomial's first order polynomial, straight line, I'm just going to stack columns of zeros and ones, and then the first powers of x. If it's quadratic, I'm going to stack columns of ones and then x's and then x squareds, and so on and so forth. So that's the first thing that I changed. So that allows me to use my equations for the least squares fitting with polynomials rather than just a straight line. The other thing I changed was I added these 2 lines. I want to deal with the uncertainties. I've read in the uncertainties, the standard deviations on the data points, they're in the vector S. I want to construct from the vector S the weights on the data points. You know, if a data point has a larger uncertainty, we tend to weight it less. As smaller uncertainty, we weight it more. So 1 over the standard deviation squared is how we weight the data. So it prefers to weight the points where the uncertainties are small, the weighting to be larger. And prefers not to weight the data points where the uncertainties are large, where the weight will be small. I construct from this, it's not very clear, but this is a lowercase w. Out of that, I build a matrix. That builds a diagonal matrix where the diagonal elements are these weights here. So this uppercase W is now that weight matrix. So that's the second thing I built. Okay, so summarizing that, I've made a new, in modifying the last code, I've made a new Vandermonde matrix that defines the model space, allowing me to fit polynomials, and I've made a weights matrix that contains the weights of the data points derived from the uncertainties on the data points. In the last class, we then calculated the best fit parameters by this little code fragment here, where we were using the linear algebra package in NumPy. We used a function dot when we were multiplying matrices or matrices and vectors. We used the function inverse when we were taking the inverse of a matrix. There's actually a more compact way of doing this, and I've replaced this kind of old language for doing this with this new language down here. So this one line calculates the best fit parameters, best fit parameters for the polynomial fit to the data using the formula in my slides. So that's this line here, and then this single line here calculates the uncertainties and the covariances for the best fit parameters based on the equation in my slides. This this ampersand here is a shorthand for the matrix multiplication. In the last class, we were using the dot function. So this is just a shorter way of writing it. Instead of dot transpose, I'm just using this dot T here. This is just a shorter way of writing it. So they call this, I learned, syntactic sugar. You know, there's no difference in the functions I was using in the last class compared to the functions I'm using in this class. There's just a more compact way of writing it that makes it hopefully easier to read. It's easier to write and easier to read. So you're just reading the ampersands as matrix and vector multiplication, and the dot T as the transposes of different matrices. So my entire calculation has come down to just these two little lines here for solving what is a sophisticated problem, right? Is the linear least squares fit to a polynomial where the data points have uncertainties. You see that I'm incorporating the matrix, weights matrix into the slides. So it's a very nice way of compactly writing this to fit to a polynomial. Okay, now we've done the fit in these two lines, defining pars and the covariance. I calculated a few more things from the fit. So this product, this is the van der Waals matrix and the parameters vector. That product is actually defines the best fit line polynomial through the data. So YF is a vector. It's a vector that exists in the model space. It's the best fit to the data based on the model space. You can think of YF as a projection of Y, the data itself, which is in the data space, onto the subspace that's the model space defined by the van der Waals matrix. So Y is a data in the data space. It's the observed data, measured data, and YF is its projection, kind of shadow into the model space that you've defined by your polynomial, defined by your columns of your van der Waals matrix. So that's a handy way of thinking about the best fit and the original data as these two vectors in these two spaces. And one's a projection off from the data space onto the model space. The difference between them, this line here, I'm not sure I calculated the residual from last class, but this line here calculates another vector we're going to call the residuals vector. So it's the difference between two vectors. One was the original data, and one is the projection of that data vector onto the model space. This residuals vector is the difference between them. So this is a vector that is orthogonal to the model space. It's kind of the component or the piece or the part of the data vector in the data space that doesn't project onto, doesn't have a component in the model space. And so that's a very important vector when you're doing fitting. It's the difference between the data vector. The best fit vector is a residuals vector that's orthogonal to Y and it's orthogonal to YF, the model space. And it tells you the, you know, what's left over when you've done your best fit to the data. I'm calculating a chi-squared from it. The chi-squared is sometimes defined as just the squares of the residuals, which is the sum of the squares of the components of the residuals vector. Or sometimes it's defined as the sum of the squares of the residuals divided by their data points uncertainty. That's what I've got. That's what I've got here. You think of that chi-squared vector. That chi-squared, which is not, sorry, it's not a vector, it's just a number. It's kind of the squared length of the residuals vector. So the bigger the squared length of the residuals vector, then the bigger the chi-squared. The smaller its length, the smaller the chi-squared. So you know the residuals vector is this vector that's orthogonal to the model space. It's the bit not accounted for by the model, and the chi-squared reflects the size, squared size of that vector. Another important quantity that I'm calculating here, with a certain number of data points. I don't know, it has more than 20 data points. We have a certain number of parameters in our model that might change if I do a linear fit compared to a quadratic, compared to a cubic fit, and so on and so forth. The difference between the number of data points and the number of parameters in the model, that's what we call the number of degrees of freedom. And often we will calculate the chi-squared divided by the number of degrees of freedom, the chi-squared per degree of freedom, because that is a measure of the quality of the fit, whether the model accurately represented the data or whether the model is insufficient to represent the data. That's reflected in whether the chi-squared per degree of freedom is 1 or is not 1. So it's a discriminant. Chi-squared per degree of freedom is a discriminant for the quality of your fit. Anyway, so I added those two lines. The rest of this cell is just printing out the results. So I won't walk through the print statements and plotting out the results. But let me just talk about the printout. So upstairs here are the I did a linear square. Did I run that cell? I don't know whether I ran it or. Yeah, okay, so let's go back here and let's just run this case. So I set this all up to handle a polynomial and handle the individual uncertainties on the data points. But I've just run it with the polynomial being a first order polynomial, what we did in the last class. So this is going to give us what we did in the last class. So here I'm writing out in the first column is the best fit parameter values, and in the second column is the uncertainties and the best fit parameter values. So this parameter here is the offset, and this second parameter here is the slope. And the offset is close to 0. It's 0 within its uncertainty. Which is, you know, what that data look like. If a galaxy was 0 distance from us, it wouldn't be receding from us. The slope is this roughly 4,000, and that's I think that's the slope that we extracted in the last place. Although something's weird about the uncertainty.
I noticed something.
Yeah.
Just in your code, you named the covariant matrix COVS at one point, where it should be just COV. Oh, wait, that's just the print.
No,
in the for loop, you did this.
In the for loop, yeah.
Oh, in the for loop.
Like one more, yeah, that one.
Oh, yeah. Thank you.
I don't know if that would hit.
Yeah, well, let's,
Oh, it did.
yeah. You're fixing it. That's fantastic. I don't know how it did. I don't know how it actually ran. I don't know what it did. Okay, but that's good. That's really great that you fixed it, because I wouldn't, no, that would be the end of the class. This is me fiddling around with the code before the class, which is never a good idea.
Remember the golden rule, do not touch the code before class, and what did you do? You touched the
I
code.
did that. Touch the code before the class, because I wanted to beautify it, something like that. Okay, so going back to this, we got an offset that is, it's changed this, it's changed both these, that's it. This offset is, 0, close to 0, as we expected. The galaxy's on top of it, like the Milky Way is not moving away from it. So, and then here's this slope of 4,000, which the inverse is the Hubble constant. It itself determines the lifetime of the lifetime of the universe. And here's a reasonable uncertainty. Downstairs here, I just printed out some other information. Now we can calculate the chi-squared per degree of freedom, because now we are incorporating the uncertainties on the data points. So we can use chi-squared per degree of freedom as a discriminant about whether this was a good fit or a bad fit, too good a fit or too bad a fit, for example. The chi-squared per degree of freedom should be 1 within some uncertainty. And the uncertainty is actually, the rule of thumb is that it should be 1 within an uncertainty that is 1 over the square root of the number of degrees of freedom. I have about, I don't know exactly, I didn't print out the number of degrees of freedom, but I had about 20 something data points. And then I have a few parameters. And so it's something like 1 over 20. And so, maybe it should be 1 within plus or minus 0.2 or something like that. And so this seems an adequate chi-square, I would say. Here's the, I didn't label it, but here's the covariance matrix that gave me all the trouble. So that's not much new from the last class, except we have a chi-squared to discriminate whether it's a reasonable fit, and it was actually a reasonable fit. But I can also go on in change the order of the polynomial, and we should be able to just run this. Now we're fitting a quadratic. And if I run down here, I mean, I'll just show you the fit seems reasonable. Now we got 3 parameters. We got 3 parameters where the first one is again the offset, the second one's the slope again, and then the third one is this quadratic term. So this x squared term. We've expanded our model space. We expanded the van der Waals matrix. We expanded the model space and the opportunity to model our data from the data space. A few things that are interesting here. Well, we still have an intercept at 0, basically. We still have a very similar slope, but you notice the uncertainty's got a lot bigger. And we have a non-zero value for the quadratic, but it's consistent because of the large uncertainty. It's consistent with no quadratic term. So I think what's happening here is that, we're looking at this low Z data, looking at Hubble's original data, in which we saw a slope and evidence for the expanding universe. But we didn't see anything he didn't see, and we don't see anything beyond a slope and evidence for an expanding universe. There's no evidence here for a quadratic term. what's happened when we added the quadratic term in, we expanded our model. The data didn't seem to need the expanded model. And because the data didn't need the expanded model, we're kind of getting into a world of overfitting. Now, this happens a lot in machine learning. It's an important feature of machine learning. And we are overfitting the data because we are fitting the data with a model that incorporates more degrees of freedom than is needed to fit the data. So that's reflected. One way you often see that is you see the uncertainties as you add additional parameters to a model that are not needed to fit the data. You'll see the uncertainties on the data points grow. And you'll also see that the chi-square can grow. Chi-square, the degree of freedom can grow because you're adding parameters, you're expanding your model, but it's not needed. It's unnecessary. So the chi-square will grow too. And I think that's what we've just seen here. This uncertainty on this slope tells us the universe is expanding, is now a larger uncertainty. This chi-squared, the degree of freedom, also has now grown because we added a parameter that wasn't needed. So that's what we're seeing when we're fitting this low Z data. We didn't really need a quadratic term. So it really didn't help the fit. We'll see it more. We can try this now. We can go and fit a cubic. Just add that to the fit. Well, we got the intercept, we got the slope, we got the coefficient of the quadratic term and the coefficient of the cubic term. Now you see dramatically the case of overfitted. There's no need for a quadratic term. There's no need for a cubic term. We're throwing in the quadratic and the cubic term. What is happening? By expanding the model, we are overfitting the data because the extra terms in the model are not needed by the data. We're seeing it in the fact that the uncertainties on the parameters of the model are growing. They dramatically grown here. This is 10 times bigger than the linear for the uncertainty here. The uncertainties on the unneeded parameters, right? They're just larger than the values of the unneeded parameters, indicating that the parameters are completely consistent with zero, statistically consistent with zero. We're also seeing the sort of incrementally, again, this chi-squared is growing as we expand our model, we make more sophisticated, more complicated model. We don't need those sophistications or those complications, so it just inflates the chi-square. Again, this is a common feature of overfitting of data. Any questions on that? Because then I'm going to go back to my slides.
Well, I'm just interested, maybe I have something wrong and you don't have to get into it, but I'm getting a higher chi-squared for quadratic fit, or a lower chi-squared for the quadratic fit than the linear fit. And I'm just wondering, is it more about like the situation that you're in? That matters?
Yeah, so let me make something. It's a good point, you're right. I should say something. I'm fitting the low Z Hubble data.
Right.
So I'm fitting Hubble's original data. And in the homework, if you look at the homework, which is a similar problem to this,
Right.
it's fitting the entire Hubble data that includes the supernova data. So and this is the whole story about expanding universe and accelerating expanding universe. In the original data, which is what I'm putting here, there's no evidence that there's evidence that the universe is expanding because there's a linear term, but there's no evidence that the universe expansion is accelerating.
It's a constant Hubble.
Yeah, so it just fit by a straight line and you don't need any more. In the full data, I'll come to in the homework problem where you're fitting the full data set. So that includes the variables and the supernova, you extend way out in redshifts. And there you need a quadratic term as well as a linear term to get the best fit to the data. So if you're fitting that, you're going to get different results from me. You're going to find that the linear fit underfits the data, meaning you get a poor chi-square because it's insufficient to fit the data. You would, for example, see systematics in the residuals, which is a typical result of underfitting. The model is inadequate to correctly fit the data. Yeah.
Could you make like a graph, like let's say we had a completely different set of data. Could you make a graph with this this method of like chi-squared against the polynomial order?
Yeah.
Could, and
Yeah.
that would be a good way of seeing.
Yeah, that would be a good way of, because you want to know if your model is complete or if it's incomplete and you're underfitting, or if it's over complicated and you're overfitting.
So I imagine it looks something like.
Yeah, you can plot the chi-squared against the parameters in your model. You can plot the uncertainties on the parameters in the model. Let me, to better answer that, let me just go back to the slides, because I think I kind of got a partial answer to that. So your question was exactly, when am I satisfied that I've got a model that is an appropriate model for my data? It's not underfitting the data because it doesn't have something, or it's not overfitting the data in that it's got too much. Simple models, or if you have too simple a model that's underfitting, it's because it's too restricted and it can't capture the signals in your data. And if you have a too complicated model that overfits, it's too flexible, and it will start to absorb noise into its parameters. So the systematics of underfitting shows up as trends in the residuals. So a systematic trend in the residuals, rather than just noise in the residuals. And it shows up in a chi-squared that gets bigger than 1 because you can't fit the chi-squared per degree of freedom because you can't fit the data. Overfitting shows up as high correlations between parameters in the fit. It shows up as inflated uncertainties on the parameters, and we saw this one. I did print out the covariance matrix. It does also show this one, that there's the off diagonals in the covariance matrix, so show these really big correlations. So these are the ways you discriminate it. And your idea about plotting versus polynomial order, that would be a great way to do it. Plot your chi-square, plot, say, the errors on a parameter, and it'll discriminate them. Okay. So that fitting I described there is is a method that works for when you have what we call a linear model, when you're doing a linear least squares fit, which means that the model is linear in the parameters of the model. Least squares fit is linear in the parameters of the model. So the coefficients of the polynomials, the function that we were fitting, the polynomial that we were fitting, is linear in the parameters of the model. So, the offset parameter, the model is linear in that parameter. The slope parameter is linear in that parameter, and the curvature parameter for the quadratic term, linear in that parameter. But maybe you've got a model that has parameters that the model is not linear in. A simple example would be, supposing you're fitting, it involves an exponential, e to the a some parameter times x. Well, suddenly you're not linear in that parameter. Another one would be supposing you've got sine AX. Okay, A is your parameter. Again, you're not linear in the parameter A. And all this framework, all this matrix, vector, or linear algebra framework, it is derived for functions where you're linear in the parameters. And if you've got functions where you're not linear in the parameters, like sines or cosines or exponentials, then there is no simple analytical solution to the problem. And so we're going to have to do the least squares fitting in a different way. And the different way that it's done is to, rather than just solve analytically for the best fit values of the parameters, which is what we've been doing, to incrementally, step by step, find the best fit values of the parameters by a walk or steps through chi-squared space, step through chi-squared contours to find the minimum value of the chi-squared. And so that's non-linear least squares fitting. And so that's what I've got a few slides on here. So here's the basic problem. Here I'm imagining we've got we want to do a least squares fit of a model to some data where that model has two parameters. I call them M and C. I shouldn't have called them M and C because I'm thinking about a case where my model is not linear in those two parameters, so that I can't use the methods we use up to now. But anyway, we've got a model, two-parameter model that we're trying to fit to some data here. And it's non-linear in those two parameters. Here's a picture of chi-squared as a function of those two parameters. So you could imagine, say, C horizontally and M vertically, something like that. So the two parameters are the two axes here, and the curves in blue are equipotential curves. So it's like a map of the chi-squared terrain. This is a valley in the chi-squared terrain, or a well in the chi-squared terrain. This is where the chi-squared has its minimum value, and this is where the best fit values of the parameters live. So we want to find the best fit values of the parameters. We want to find this minimum. The way that we will do it is by guessing best fit values for the parameters. We'll just start with some guess for parameter A and parameter B, or parameter M and parameter C. And then we'll figure out what the chi-squared is. And then we'll use some algorithm to change the values of M and C, the two parameters, in an attempt to try and step our way or walk our way to the chi-square minimum. And so this is going to be an iterative method where we'll take many steps, walking our way from some initial guess for the values of the parameters to the location where the chi-squared is minimum, and that's where the best fit values of the parameters are. So this is a very different method, very sort of non-analytical, numerical stepping method to find the best fit values. Look, we've done a lot of work in the past on random walks, for example, on Taylor expansion, when we're talking about random processes, or we're talking about differential equations that would allow us to take steps through a function, the chi-squared function. And the things that we've learned in the past about random walks and also about Taylor approximations are typical ways that this stepping from some initial guess to find the chi-squared minimum are done. So here I've got 3 slides that will look very similar, but they're just advertisements for several names of several ways that you can descend from your initial guess on the chi-squared mountain to the minimum, to the valley to the chi-squared valley. So we've got to make this descent into the bottom of the valley. And what ways could we imagine you might do it? One of them's called, name is stochastic descent into the valley. This involves taking a random walk through the valley and working your way in kind of randomly. And we met this sort of way when we were talking about random processes. So the way this method works is you might take imagine this chi-square contour. Imagine I'm starting out here with my initial guess, and then I just randomly walk off in some direction, a certain step. I randomly walk off and I ask myself the question, how much did the chi-square change? And I might have some rule like, well, if the chi-square decrease, I'll accept that step. I'll stay there. If the chi-square increased, then I'll reject that step. I'll go back. And remember, we did that in Markov chain Monte Carlo. We would step through the states of a ferromagnet or the states of a volume of gas. We would make a step in those microstates. Here I'm making a step in chi-squared. We would always accept it if we went down in chi-squared. Or energy, or whatever parameter, or we might reject it if we went up in chi-squared or went up in some other parameter. So this is one way of finding the minimum, is taking random steps around and accepting or declining depending on whether you go up in chi-squared and down in chi-squared. So that's called a stochastic descent, and that is used in machine learning, for example, and on various chi-squared minimization problems. Another method is, which might seem a smarter method, a more straightforward method, perhaps, than randomly walking around and hope you get down to the village, is what's called gradient descent. So in gradient descent, again, you've got the same problem. You've got a space of chi-squared, 2-dimensional chi-squared here in my little picture. We've got these contours. We want to find the valley or the hotel or the pub that's down here. And we're starting out over here on some location that we were dropped into. We're going to, at that location, we're going to compute the slope of chi-squared. So we're going to compute a little vector that represents the slope of chi-squared, and we're going to take a step in the direction of that slope, the downward slope. And so this involves calculating the slope of the chi-squared here. We're going to use the first order Taylor expansion, which we've met before. For example, in the Euler method for solving differential equations, we're going to use that first order Taylor expansion for estimating the slope and enabling us to take a step in the direction of the slope. And then you keep on doing that. You keep on figuring out numerically, approximately, with first order Taylor expansion, you keep on figuring out the slope, and you take steps downward and downwards and downwards. So this is another approach, and that's called gradient. Here's one more approach that I put in the slides. This is called Newton descent. So this is just a little more sophisticated case. So in the gradient descent, you just use first order Taylor approximation to numerically calculate the slope. And you take a step in the direction of the slope downhill. In the Newton method, you use, it's effectively the second order Taylor approximation. And so the second order Taylor approximation uses the differential of the function, the chi-squared, and it would use the second order differential of the function, the chi-squared here. And we use the Taylor expansion in the second order Taylor expansion in the Newton method. It's used to calculate not only the slope, numerically calculate the slope, but also the rate at which the slope is changing. So for example, if the slope is changing dramatically, right, you might want to take a big step, because you can see it's changing. I mean, that doesn't make sense physically, but you want to, it looks like you're far off from the minimum, so you would take a big step. If the slope is if the slope of the slope or curvature is changing slowly, seems like you're getting near to the minimum, so you might want to take a small step. So the Newton method accounts for both the slope in taking your step in chi-squared space, and also the rate of change of the slope, the curvature. It takes into account both of those. So in short, we can't solve the problem if you've got a nonlinear model, a nonlinear function with the analytical method, with the method involving the matrix algebra to calculate best values of the parameters and their uncertainty. Rather, we've got to find the minimum chi-square and the values of the best fit parameters by walking through, taking steps through the chi-squared space. And I'm just trying to give you a flavor of a whole world of different ways that scientists have developed for walking through chi-squared space to find the minimum. You know, looking at the three examples that I gave you, the stochastic descent, the gradient descent, the Newton descent. You might say, well, why don't you just always use the Newton descent? It seems like that's the most sophisticated. That would be the best one to always use. And often it is the best one to use, but it's not always the best one to use. I'll give you one example. For example, this random walk, the stochastic descent. If you use that method, you can avoid problems of getting trapped in local minima. So one problem with a chi-squared function, not for the one I've plotted here, this just has this minimum here. It's easy to find it. But you might have a chi-squared that has, you know, a true minimum, but also other surrounding local minimum, other valleys that aren't so deep. With gradient descent and with Newton descent, you can get trapped in a local minimum. With this stochastic descent, this sort of Markov chain Monte Carlo, you can walk your way out of a local minimum. And so it's a way of getting out of a local minimum and allows you to find the true minimum. Now, the other compromise is how many steps do you have to take? Typically, a stochastic descent involves, because randomly walking around, it's not generally the best way to get down the mountain. It's going to take a lot of steps. It's going to consume a lot of computing time, a lot of computing energy. So if you have a simple chi-square function, it's better to do like a Newton descent, because you'll get down in less time, expending less energy, or you get down expending less computer time and less energy. This is the problem with all the AI, right? That you know, that it's a lot of what it's doing is minimization, is gradient descents, and it can be very, very time consuming. And so that's why AI is energy, it consumes a lot of energy, it consumes a lot of time. It is in that sense expensive. Okay. Yeah, I think I was just going to show you a few examples. Um, this is just a few cells of code where I've got a few examples of gradient descent, Newton descent, and stochastic descent, just so you get an idea of how you might code these. You're going to be using these for when you run CurveFit, it uses these, and often it uses a combination of these. It might use a combination of gradient descent and Newton descent in the fitting that you'll do of the Hubble parameters. So this first cell here, I'm just defining some arbitrary chi-squared space, right? That's completely made up by me. I'm going to imagine a chi-squared space, and it's going to be a chi-squared that only depends on one parameter. And in these examples, I'm just showing you the descent as if there was just one parameter in your model. So you imagine that, if this was really a straight line, this would be a chi-squared that's a function of two parameters. If it's a quadratic, it'd be a chi-squared that's a function of three parameters. Or if you're actually fitting the data that you have or the theory that you have, then you might have many parameters and a chi-squared that is a function of many parameters. So I'm just taking some simple illustrative case. So my parameter is n, and the chi-squared is this function of n. I just made it up. I randomly made it up. But I made it up so, not completely randomly. I made it up so it is some sort of well, right? It is a well. You could start off in the high altitudes of the well. And to find the chi-squared minimum, you would need to descend to the bottom of the well, the valley. And we're going to look at the various ways that I've discussed for descending from high altitudes in chi-squared down to the bottom of the well, where we find the magic best fit value of the parameter that chi-squared is a function. So that's the goal here. We want to find the value of n and the chi-squared at this location by taking a descent by these methods that I've advertised. Okay, so the first cell I've got is gradient descent. And I'm giving these examples just so you can see a little bit more concretely from the slides about how you would what algorithm the descent uses, and also, well, what are the parameters of a descent? It's a bit more complicated now because you will have to pick certain parameters when you use a gradient descent or when you use a stochastic or a Newton descent. There are parameters associated with it, and you have to choose those parameters when you're doing fitting, and you might, you have to choose the right parameters for the type of descent. Okay, so upstairs here are the parameters that I'm picking. So this would be typical of a gradient descent. I'm not going to get through all these 3D sets. I would pick an initial guess. Right? You've got to guess an initial value parameter, so that's m0. If you're going to do a gradient descent, you're going to take steps of a certain size in a direction that you're going to figure out in Taylor expansion. So you need a step size. That's what h is. So you've got to pick a step size that's appropriate. You don't want to pick it too big. You might step over the valley across the entire valley. You don't want to pick it too small, or you'll be walking around forever in the trees in the valley. So this is the step size. You pick a tolerance. You're trying to find a minimum chi-square. But it will take you infinitely long to step around and find the absolute minimum chi-square. So you've got to say, oh, this chi-squared is adequate for me. This chi-squared has not changed by some tolerance. You can set the tolerance that way, or you can set the tolerance by the parameter does not change by this amount, more than this amount. So there's some sort of tolerance that you use. And then also when you use a gradient descent, you'll set a maximum number of trials. Okay? So you want to stop the computer looking for the minimum after some period of time. You don't want it to go on forever. And it may get stuck looking for the minimum. So you normally set a maximum number of steps, a maximum number of trials. So when you use gradient descent in, say, CurveFit or in some other program, these are the parameters that are behind the scenes that are determining that you're picking and determining the type of gradient descent. So downstairs here, what I'm going to do in my gradient descent is keep track of. I'm actually going to keep track of the parameter as I pick the step. So I'm going to watch the descent. You don't normally see this when you're doing a fit with some commodity program. You don't watch the parameter changing. And I'm also going to see how the chi-square changed as the parameter changed. So I can do this because this is my own code. So this mi, I as an index is going to hold all the values of m as I step down the mountain towards the valley. And I initialize the first value of it to be m0. Now I'm going to do the gradient descent. The gradient descent I set up a for loop over the maximum number of steps that I'm going to take. Now, I might break out of the for loop early if I decided I've reached the minimum. Or if I don't, inside the for loop, decide I've reached the minimum, I'll go through the entire for loop. But anyway, I'm setting up to do a certain maximum number of steps. So that's why I need max trials. I jump in the for loop here, right? Here's the step I'm going to take. It's actually this step size times the gradient, right? And I'm going to calculate the gradient with a function. I'll have to go back up to it. So this is where the Taylor expansion comes in. I'm going to calculate the gradient at the location I'm at right now, approximately by Taylor expansion. And then I'm going to take a step in proportion to the gradient and its product with this parameter here. This means that if the gradient is steep, right, I'm going to take a big step. If I'm on the mountain, again, this is not a safe thing to do, but this is an efficient thing if you're a computer trying to get down to the minimum. If you see a big gradient, take a big step. If you see a small gradient, says you're near home, just take a little step. So this is what's happening here. So I'll go back to this. This is calculated in a user function I got. I'm going to take a step determined by the gradient there, and it's in the direction of it would be in the direction of the gradient, downhill for the gradient. Here's the minus sign to make it go downhill. And when I take that step, I'm going to I've adjusted the value of m. If the value of m, the parameter of the model, has not changed by an amount we call the tolerance, if the step size is small enough, I'm going to break out of this loop. And so that's how I decide when I've got to the minimum. When this step size is small. So we go around this and I'm taking all the steps and I will eventually either break out because I've reached this tolerant, or I will do these 5,000 steps. The gradient itself, as I said, was actually calculated up here. I skipped over it. This is the first order Taylor expansion. So this is where I'm using the Taylor expansion to calculate the gradient. Because remember, in my example, I defined the chi-square function. I could easily calculate the gradient by differentiating it. But in your real model of the data, you don't know the functional form and you can't calculate the gradient. Okay, so if we run that, this is where I started. I started at n equals 1. You remember the chi-squared function? It was a constant plus something m squared plus something n cubed. Its minimum is 0. These in magenta are all the little steps down the chi-squared through the chi-squared contours through the chi-squared space. That's a function of the parameter n, and then it recognized based on the torus and this green point here that it got to the minimum. So we walked down the hill. It took a lot of steps. You look, they're a little bigger at the top, the smaller at the bottom to find this minimum. You know, even within this case, there's a bunch of parameters you could adjust, right? If you pick the wrong size for that parameter h, you could be making 2 big steps and you could jump over the minimum, or you could be making such small steps that you run out of trials and trying to walk downhill. So it's important to recognize when you do this iterative methods that you have to tune your parameters for your particular problem.